quick update of the status of things. Let me share the screen. I'm sharing the screen. That's super. Okay. Number one, we have all the TAs, but are still working out their lab assignments. What screen? Yeah, okay, thank you. Although I can see it. Whatever. Okay, so we have the TAs, we know who they are. They have accepted their, position, which comes with a very nice tuition waiver for international students. Anyway, we have them. We'll get it worked out. We'll update the syllabus later this week. Hopefully, I get all that information back by tomorrow, and it'll be prepared for Thursday. That'll be good. But if not, there's no labs till Tuesday anyway, so whatever. We'll get it sorted out. Number two, expect to learn more about Packback starting Thursday, right, on Thursday. So there's that. Packback, again, that online question and answer platform. I still gotta follow up with the guide because they mixed us around with some of the sections, so I don't have access to the ones I should have. Some ones have to be created because there was an additional hidden section that I got thrown into here. We'll work it out. It'll get done. There's plenty of time to get it done. It's not a panic, but I plan to introduce Packback anyway next Thursday, and hopefully it'll actually be all up and running by the weekend. So we shall see about that. And number three, of course, we got lecture, right? So today, finish photo management and just make a tiny dent in newsfeed. Now, some of you may have noticed, hey, there's no lecture notes for these other two Facebook lectures. Yeah, I don't know how that happened. I got so caught up sending out the lecture notes to everybody else that I didn't post them up for the other ones, but I posted them there this morning. They're there. If you go to Blackboard, which is here on Blackboard, if you go there, you'll see they're up. Okay, so, and this is the other section, but still, whatever, they're there. Facebook module, the notes documents are there now. I posted them for both sections that I got. Okay, so let's do this, let's get it done, and then we can all go on with our lives. All right, so let's see where we left off here. Somewhere about halfway through. Disk drive versus RAM, hybrid database. Okay, so this is the example we talked about. I'll just start here. Okay, so remember that what you often find in real life is that businesses have a huge pile of data. Some of it, a fairly small fraction of it gets looked at a lot. Most of it just sits there. I mean, for example, suppose you get old and you have a bunch of financial information somewhere, right? You have like an investment account online and you have statements going back decades, right? Obviously, there's probably no reason why you would, go back and look at your statements from, fourth quarter 2022. You might, they keep them there. They might have to keep them there for legislative requirements for a certain time. But yeah, realistically, nobody's looking at them, right? So it doesn't make sense to store those things in RAM for super fast response time when chances are nobody's going to be looking at them. Same kind of thing with a lot of systems. With Facebook's photo system, photos that are years old, you tend to not want to store those in RAM because mostly people aren't looking at them, right? They're old news. So this is a common kind of setup. Again, like I talked about at the end of last lecture, you'll have your popular data for whatever reason it's frequently accessed. You'll store that in RAM, and then your less popular data, you'll keep on disks. And, however much your budget is for a big block of RAM, you'll store as much data in that as you can. Okay, and typically real world numbers, they call that the cache, the RAM cache, because it's easy to get to. Usual numbers for like hits in the cache, somewhere north of 90%, right? So they try to say our business model, in order to make most of the people happy, we want to have the vast majority of requests be immediately serviceable through RAM, right? Because it's kind of one of those 80-20 type situations. 80% of the traffic is for 20% of the data, that sort of thing. Get 90% or so, that they usually consider that to be pretty good. All right. Now, This is the same kind of thing, right? Just more about that. In-memory grid is one model for doing that, right? So in-memory grid, it has the same RAM as in your computer, but there's just a lot of it. You know, your computer might have like 16, 32 gigs of RAM. Here, you know, they have many terabytes of RAM at least, right? And then that means the system can operate at RAM speeds for any hits in the cache rather than disk drive speeds. And again, back in the old days when disks were mechanical, not like solid state drives like now, potentially thousands of times faster, right? RAM being electronic, vastly faster than any mechanical system. Of course, you still need to do backups, right? So even if data is stored in RAM, right, it's stored in the cache for fast access, you still need to have a backup copy on disk because RAM memory is volatile. If you lose power, everything gets erased, and it would be kind of a train wreck if somebody, you know, for whatever reason you lost power. And again, there are variations on non-volatile RAM systems, but you know, in those days, you know, usually done on disk drives. Those are solid state drives now, but okay. So that's a little historical context for what we're talking about for Facebook's Haystack. Now, next question is replication. So before we get into it, we got to talk a little bit about backups. So replication just means making copies of something. So imagine that your organization has 10,000 or so servers for global application users, right? So it's got tens of thousands of servers, different data centers around the world. Question is, should you put them all in one massive data center at one point on Earth, or should you scatter them around in some way and operate multiple data centers? Well, one thing that you'll find is if, first of all, what if your data is all stored in one massive central location? You're going to find that there's going to be delays for distance, because those electronic signals going through the network, at minimum, they tend to get a delay of about 1 millisecond per 100 miles, right? Those electrons, they don't teleport. Even if you have a system with really fast with a lot of bandwidth, you can push through a lot of data per unit time. The transit time itself isn't going to change that much. It's still going to, it's kind of like high bandwidth is like having a highway with a lot of lanes, so it can push through a lot of cars over a given stretch of time. But the cars are still going to be limited to going like 60, 70 miles an hour because they're cars, okay? So there's that. Number two, if for whatever reason there's a traffic spike, whether it's because of some real world natural thing that a lot of people want to access the data, or if it's because there's some sort of attack going on, some kind of denial of service attack, it's going to affect everybody. So that's potentially kind of bad. Third point, optimized availability is less effective. Well, I will talk about this for a minute. Draw a picture screen. Thank you. Okay. So I talk about optimizing availability. Imagine that you are storing data for everyone on Earth. Okay? Everyone on Earth. But suppose the vast majority of your users during the day, we're gonna do a few curves here. Great. Okay, we're gonna make some curves. A little bit of overlap. A little bit of overlap. Okay, so this is time of day. And suppose that this is your demand in the US, this is your demand in Europe, which follows, 9 hours or 8 hours or so after the US. This is your demand in Asia, which follows, 8 hours or so after Europe. So what you're going to see is there are going to be different spikes. Now, if you want to optimize availability for Europe conventionally ends with an E. Don't know how that happened. All right. If you're trying to optimize availability by storing popular information in the cache, what this means is you're going to have to refresh it a lot, right? You're going to have to be moving stuff to disk, moving stuff out of disk a lot, because what you're going to need during this window is basically what's popular in the US. What you're going to need in this window is what's popular in Europe, which is not going to overlap very much with what's popular in the US. And the same thing for Asia, right? So always you're going to have to be kind of churning your popular data. However, if you just store data for one group, right, for the US over the day, say, then your curve is going to look something like this, right? So I'm going to cross this out. Everyone just in the US or just on the West Coast, better yet, right? Then it's going to look more like this, right? So you have like a busy time and you'll have a quiet time. But what'll happen is, even though you have busy and quiet time, the overall distribution of popular data will be very similar. All right, so anything popular at 8 a.m. probably still popular at 8 p.m. Does that make sense? I hope it does, right? Because everybody, if you're on the West Coast, you're looking at West Coast stuff, right? You're looking at what the Dodgers are doing, or you're hearing about the latest earthquake or drought news in California, stuff like that, right? But whether you're looking at that stuff during the middle of the day or at night, it's not going to change that much. So you're not going to have to update your cache nearly as often. So it's a lot simpler to manage a smaller, more localized data center. Not really just because it's smaller, but because it's more local and the distribution of what's popular stays the same over the course of the day. Okay. Anyway, and last note, potentially brittle reaction to failure. Imagine if there's an earthquake, there's a fire, your network cables blow up, there's some sabotage, there's some disgruntled employee that digs up some cables, cuts through them with a chainsaw, I don't know, right? Then that's pretty much the end of your operation. It's a lot harder to coordinate that kind of attack, or have that kind of catastrophic damage if you have multiple data centers. One data center goes down, you redirect traffic from other data centers to backup locations. So in general, it is a good idea to adopt a decentralized approach. You don't want to put all your stuff in one place, because even though in some ways that sounds good, you'd think, well, I could save on hardware costs, I could save on building costs, facility management costs. Yeah, that's true, but it creates a lot of actual problems for the system implementation. Okay. So solution, like I said, is generally for replication is to use decentralization. So you have multiple copies of the data stored at separate server groups called data centers all around the world. And if one data center doesn't have something that somebody's looking for, they can forward the request somewhere to another data center. For example, this is what Google does. Google has a bunch of different data centers storing copies of web page data that they use to deliver search results. The internet is so big, it would be kind of crazy to have a copy of every web page's data at every data center worldwide, because they got something like 20, 25 data centers. We'll see what it is by the time I actually start the Google module. But anyway, they don't want to do that, right? Because most places in the world, based on language, they're not going to be looking at sites in another language very much. They're not going to be looking at all those pages. If they're in Europe and they're speaking French or German or whatever, they're not going to be looking so much at English language pages. Likewise, in the United States, vast majority of people speak English with a substantial chunk of Spanish speakers. That's mostly the sites that they're looking at, right? They're not really looking at, say, Chinese language websites. Most people in the US can't read Chinese, so what would be, yeah. Anyway, so there's that. So you don't really want to store a full copy of everything you're storing at every data center. Data centers should just store the stuff that's locally popular. So advantages of that approach: number one, less latency. You get your responses faster because the users are physically closer to the data center they're interacting with, right? Locally important data, it's easier to cache. It's easy, you can do it continuously. Like I say, you don't have to do that constant churn throughout the day. If there's a system failure, it only affects the local system. And also, your database size is going to be smaller, so it does get a little bit easier to do updates. If you want to do something like change the structure of your database or do some major overhaul of the system, yeah, it's going to be easier to do that. Okay, so that's why we prefer decentralization. Now, as far as replication for Facebook, there's some specific stuffs here. We know, especially for a lot of users, friendships and activity are going to be correlated with geographic proximity, which just means you tend to live closer to the people that you're friends with, right? Now, you guys, you're probably in a window where that may be the least true it's ever going to be. So if you join Facebook in high school, middle school, grade school, whatever, right? Pretty much all your friends were people you knew from real life. And, you know, if you're a kid, the people you know from real life are generally, you know, in your neighborhood, right? Maybe some relatives, maybe you're friends with grandma and she lives across the country, but, you know, a lot of people are close by. As you go to college, of course, boom, right? Suddenly people go all around the world, and people that you used to go to school with, you don't, but you're still friends with them on Facebook. And because you're still in college, and you know, maybe you're in kind of that bridge where you have high school friends, you haven't made a lot of new friends locally, you still have a lot of contact with those old people that are suddenly further apart. So there is a little window where that kind of blows up. And then you get older and you kind of settle down and you have like a bunch of people that you're sort of peripheral friends with on Facebook. You're friends out of inertia because you knew them from back when, but you don't really interact with them that much. The people that you interact with are like, hey, we're going out on Saturday. Do you guys want to do something? Or, you know, here's the pictures of that trip we all went on together. So you do have friends from all around, but the people that you interact with more tend to be the ones that are physically closer. Anyway, so that's what Facebook knows. And this is handy for all the reasons that we talked about as far as where you store data. Facebook likes this model where, hey, the data that we really need, most people really need, is already supposed to be really close to where they're at. So that's useful. Anyway, they use some kind of in-memory grid system architecture, again, to make locally important data more accessible. So things like photos that your friends who live nearby have posted, recent activity, local news that Facebook wants to update you about, right? So, you know, if you're looking through your feed at some point, you may see, oh, here's some local Chicago news, right? Or here's some politician who wants money, or here's some charity events, stuff like that. Okay. So yeah, Facebook uses replication too. And again, they're a worldwide operation, even though, you know, dominant in North America, but they are still worldwide. 3 billion users, they're not all coming from the US. All right. Now this is the haystack problem. We finally get to it, as promised. So haystack was their system for storing photos. All right, so I'm gonna, let's see, can I copy this? I know I can copy this, but I can't copy it from, copy it here. Wow, that's loud. Screen. Okay, just a second. Damn it, this is harder, whatever I'm doing here. All right, let's try that again. Because I want to blow this up a little bit so you can see it a little better, that's all. Okay, now you can't really see the numbers here. I should bring my laser pointer. I have a laser pointer somewhere. I gotta start bringing that. Okay, the column on the left, that is the cumulative percentage of how many photos are involved in this graph. So at the top, it's 100%. At the bottom, it's 0. Going left to right, the x-axis, you might be able to just make out that that's age in days at the bottom, and the intervals are 200s. Okay, so what that means, if we look at, see this point here, I'm going to circle it. This point here, just short of 400. Let's make that red. Over 80% of photo requests are for 1-year-old photos. Or not over, about 20%, right? About 20%. Or for 1-year-old or more. Now, this graph, this is actually from like 10 years ago. This isn't a current graph of Facebook setup. This was, you know, this was their situation when they started implementing Haystack around 2009, right? So, like I said, about 10 years ago, this is what they were seeing. So even at that time, even that far back, they were seeing a surprising number of requests for older photos, right? So it wasn't like this financial situation where, you know, people are interested in their current account balance, and even though you have past account statements, really nobody's going back and looking for them. This is a difficult problem for Facebook because they want to deliver photos quickly to everybody, not just on request, but also when, you know, they show up in the feed for various reasons. But having all that stuff in RAM, right? There's not like a non-trivial amount. If they want to get up to 90%, that's a lot of RAM they have to carry. So this part here from, along this curve, this is the real expense part, right? They have a lot of photos that they want to keep showing, but putting all those photos in RAM when they're getting like, petabyte worth of photo data every day, that's insanely expensive. They can't afford it. Okay? So that was their situation. Anyway, so this created problems, right? And again, think back, this is like 2009. Facebook is not that huge. I mean, it's big, but it's not, it's not the situation that it is now. Okay. So what Facebook was actually doing is relying on what are called content delivery services to deliver photos for users. So I'm gonna draw a picture for that. We like picture screen. Yeah. Okay. So what happens is there are users, and the users send requests to Facebook. Okay. And the question is, how does Facebook get the pictures? Well, Facebook has the pictures stored. I'm going to draw a disk here. Damn it. It should not be this hard. I don't know what's going on here anymore. Damn it. All right, but it's going to be a good looking disk when we get it done, I promise. Okay, so there's the disk. Now, Facebook has a bunch of these. They got a bunch of photos stored on disks. These are slow, right? But Facebook, again, they're not really managing this giant block of RAM. There's a content delivery service that's managing this big block of RAM. So I'm going to draw RAM over here. And I'll use CDN for content delivery service. Okay, that's some third party. Facebook is paying them to do the work. All right, so I'll put $signs there so you recognize that. All right, so these are owned by Facebook. I'm going to put them under the blue umbrella here. This content delivery service is not owned by Facebook. All right, so what happens if a request comes in? I'll do it in green for dollars. Facebook sends them dollars, right? A request comes in, Facebook checks at some point, there's an interface. Draw an interface. Does Facebook deliver the photo, or does the CDN? Okay, that's the question. And if Facebook has it, Facebook delivers it. If the CDN has it, they might deliver it back through back directly to the customer. Now I've drawn it here so it all goes through Facebook. That architecture aspect of it isn't that important. I mean, obviously it's all going through the Facebook site. Okay. So that's the question. Now again, Facebook wants to deliver photos fast. In order to deliver them fast, it has to rely on this content delivery network service. But that's expensive, right? It's a very expensive service to provide. So Facebook is only using it for the most popular requests. But as it turns out, doing requests on disks is actually getting too slow, right? Because Facebook has to do a lot of those lookups for various purposes for people on Facebook. And so that's getting to be slow too. So Facebook simultaneously wants to, number one, cut down the reliance on CDN to save money, right? That's a worthy goal. And number two, any disk photos should be delivered faster. Okay, now of course, the hardware of the disk drives, you're kind of limited to that, but potentially you can get, these photos done in around the order of like 100 milliseconds, which isn't too bad. They can manage with that in 2009, but they still, whatever they're doing, they'd like to deliver it faster. Now, the problem was for Facebook, looking up something on disk isn't just knowing where something is and pulling that file. There's actually a lookup process. So Facebook would first have to check, is this something that we store locally or on the CDN? If it's something that's stored locally, we have to look up the access privileges on it. Like, is this person allowed to see it? Do they have edit privileges, or do they just have viewing privileges? And then they have to look up what disk drive it's actually stored in their system. And only then are they at the point where they can finally go, oh, it's in this track on this disk and we'll pull it now. Okay, so there are actually a lot of steps. Like I said, you know, big systems, things that are simple on one machine become complicated on multiple machines. So there was a whole lookup process in there. Let's get back to this. Okay, so caching all the photos in RAM, way too expensive. It's 2009. Facebook is still getting bigger real fast. They can look at the horizon and say, yeah, we can kind of afford this CDN situation now, but in 5 years, we're going to have so much more traffic and so many more photos. It's just not going to be sustainable. We got to do something different. So let's flash back to our capacity equation. If we recall, lambda equals S divided by T sub P. Remember, lambda is the arrival rate, how fast things are happening. So in this case, we're talking about how often users are requesting photos. S is the number of system processors, and T is the time required to process each request. So one possibility to deal with increasing lambda, right, increasing number of requests, is you increase S, you add on more machines. Well, obviously buying more machines and putting them in your system, that's expensive, right? All that hardware costs real money. Better, if you can do it for free, would be to reduce the processing time, right? Make your system run faster. But how are you going to do that without changing the hardware? Well, as it happens, there are a number of clever people that worked at Facebook, and they figured out a way to do it. Okay, so I'm gonna actually bounce ahead to this haystack thing. Then we'll come back to the object storage. So their simple solution was to use fewer hard disk operations to get the photos, right? I/O, input output. So they were asking the hard drive system less often, fewer requests per photo. So number one, the photo metadata was something that could be stored on RAM, right? In RAM. All the data about the photo itself is huge. You don't have room to store that. But the metadata is relatively compact, right? If you got like a 10 meg photo, maybe, you know, your metadata is just like a kilobyte, maybe not even that. And so, you know, you can store metadata for a whole lot of photos in RAM, and that saves you the, you know, that's basically negligible time versus looking up something on disk. Number two, photos stored together in large files. Remember that even if you're pulling stuff from disks, it's faster to do it sequentially if you're reading along a single track. So if you store the photos sequentially on disk in an album like they started doing on Facebook some years ago, then you're going to upload them together in the same spot on the disk, and you're going to pull them from the disk at the same location. And getting that batch of photos, you know, if somebody wants to look at an album of like 20 images from a vacation, that whole operation is going to be a lot faster than it otherwise would. And of course, encourage users to upload and download photos that way. The last thing, they actually embedded the URL of the photo. The web object, the photo's web object, actually contains that metadata, right? So they could look up instantly and see, oh, this based on the URL. So if you look at the web object for a photo, for like anything on Facebook, it's going to be this long string of fairly random letters and numbers. And you're like, hey, well, what is that? Why? That's all an encoding for who can look at it and where it's stored, that sort of thing. So as soon as somebody clicks on that, that's why I say, you know, it's in RAM. As soon as somebody clicks on it, the process for, you know, pulling all that information out gets processed in RAM. That URL gets separated into its component parts, and they could say, here's the list of friends who are able to see it, here's their privileges on it, here's where it's stored on disk. They can look up all that stuff fairly instantly. So consequently, number one, this system is really fast, especially for that long tail of older photos, right? For photos that are like 5 years old, used to be a whole long process of going through looking up everything on disk to finally find the photo itself. Now, right away, they can say, yeah, it's still stored on disk, but the processing to find it on disk, that all happens in RAM, and it's super fast. Okay, so, and of course, like I said, sequential albums are faster for, you know, a large number of photos at once. So without adding any new hardware at all, Facebook's, you know, or at least only a trivial amount of hardware, like some more RAM maybe, without adding any new hardware, Haystack's model basically tripled the system capacity pretty much overnight. So that was huge. So number one, right off the bat, they could rely less on content delivery services because a lot of photos that they used to not be able to deliver fast enough, suddenly they could. So that's saving them money. Number two, you know, tripling their processing on that, that buys them a lot of time for system growth, right? Maybe it's going to be like another 4 years before their system triples. In that time, they basically don't need to tack on any new hardware for this system because they're already managing with that load right now, right? So that was actually a really huge thing, Haystack. Now, talk about object storage. So Haystack is what's called an object storage system. We'll talk about a little bit more about different kinds of relational databases. We'll fill out the rest of this lecture. Instead of storing the data as single files that are read and written as units, a lot of times you can store the data in a way that it's broken up, right? So part of the data about something you can store in one place, another part you can store somewhere else. So for example, with photos, photos generally have the attribute that you write them once, right? You put them on disk once, but you might retrieve them many times, right? But basically you can't go into Facebook and edit the photo itself. You could delete it and upload a new one, but you can't go in there and, you know, make little Photoshop edits to a photo that's already on Facebook. So those kind of things, they need fast read times, but write speeds, not that important. But other data, like transactions, if you're buying something, that needs fast write operations. Because if you're Amazon and you're doing a whole bunch of transactions per second, and each one of those actually involves a bunch of database operations, then all those changes to the database, they have to happen quickly. So Facebook had to retrieve photos quickly. So what they do, number one, the metadata, right? Like where the photo is stored, who can access it, that should be stored in RAM, right? And in practice, what Facebook does is they embed that in the URL like that, but then it gets processed in RAM. So functionally the same thing. And the photo data itself, not the metadata, like who can access it, but the actual image of the photo, that gets stored separately, either on RAM if it's popular or on disk, you know, if it's not so popular. Okay? So that's one of the neat things about object storage. Again, you have the data itself, the photo, you can store that in one place, and then the data about the photo, like who it belongs to, who can look at it, where it's stored, that you can store somewhere else in order to be able to process it faster. And it balances the cost, because that metadata is pretty compact, right? It's like a list of a few things. The photo image itself can be pretty big. So, you know, storing the whole thing in RAM would be pretty prohibitively expensive. Okay. There's some articles if you're interested. One of these in particular, like I said, if you want to check this out, I would say this one. This one is probably the best and most readable. If you do feel like reading a little conference paper on this, Finding a Needle in Haystack, Facebook's photo storage. This talks about all the stuff that I was talking about. And again, it's fairly readable as these things go. So if you want to learn a little bit about this tech stuff, if you're like, this is where I lifted that image. Oh yeah, thank you. All right, this is where I lifted that image, for example. And you see they have some similar drawings of how the CDN is set up, you know, blah, blah, blah. Okay. So anyway, if you're interested, if you're like, hey, that's kind of neat, I'd like to learn more about that. This is the one I would recommend. But there are some, you know, there are some other articles there. You take a peek at them if you want. Okay. Now, the rest of this is going to be about our quick intro to databases. So databases are ways of, it's software for storing data, right? So a database system is the whole system, which includes software, hardware, users, policies, all that. But, you know, when we talk about databases, a lot of times we just mean, you know, we're talking about how the data gets stored. So database management system allows for storing and retrieving data. For example, in Facebook, obviously, photos, set of users who have liked a particular photo, set of all photos posted by a particular user over the previous 2 weeks. These are the sort of things that Facebook has to deal with routinely, right? Somebody wants, you know, sees a thumbnail image in their feed, they want to click on it to blow it up, get a, you know, good look at it, whatever. Somebody is looking at Facebook. Facebook says, here's an image that your friend posted from vacation, and underneath that they have a list of all the people that have liked that photo, right? Or if if you go to your own site on your own page on Facebook and you see like your list of recent activity, one of the things you're going to have to maybe see for that is everything you've done in the last 2 weeks, including all those photos. So database systems allow that kind of retrieval of data. And there are two main approaches. Number one, relational, which is what the rest of this lecture is going to be about. And number two, non-relational or NoSQL, which we'll have a couple slides about. And we'll talk a little bit more as the course goes on. So relational databases are basically like the bland vanilla default version of databases. Most of the data that's been stored in databases over the last several decades has been in relational databases, but NoSQL ones have become very important since, you know, the last 20 years or so. We'll talk about that. Okay, so in a relational database, data is stored in a hierarchy of tables, rows, and columns. So a table is a set of records of a particular type, right? So if you, for example, have a set of photos you want to store, you create a table for photos. If you have a set of user accounts you want to manage, you create a table of user accounts. And the records are the particular thing in the table, right? So if you have a table of records or a table of users, every user would be one record. Right, so the record is all the information about that one thing, and a table is a set of information about things of a particular type. Records are also called rows, and we'll show why in a minute. It's just because when you draw it out, you know, the records are given horizontally. Likewise, the columns or fields, those are the attributes of the data. So for example, if you have a table of users, typical things you might have for the users: number one, the account name; number two, the email address; number three, I don't know, some variation on the password, some scrambled version of that. All of those could be fields, okay? And every record would have them. So every table is composed of rows. Every row in a table contains the same set of columns. So here's a picture. Boom. So this is some kind of user account situation. So you have a name, you have an email for each row, you have a password for each row, you have their birthday, so when their birthday rolls around, you can wish them a happy birthday, and maybe you have some kind of link to their profile picture, right? Some sort of scrambled URL that says, hey, here's where to find their profile picture in our system, okay? So the table here, table is users in some way. Every row indicates a particular user, and every field, right, is a particular kind of data associated with a record. So remember, every record has the same kind of data, has the same set of fields. Okay, that's the basis of the relational database model. Yeah. 4 basic database operations. Number one, insert. If you want to add something to your database, whether it's a new record or a new table, that's obviously something that your system is going to need. Right? It's very common if somebody creates a new account on Facebook, you want to be able to add them to your database. Number two, delete, right? If something goes away, fine, you get rid of it. You don't want to have your database clogged up with data that nobody's using because, you know, it's done with. Modify, of course, you often need to change the contents of databases. For example, somebody enters in their birthday and then they realize, oops, I entered in the wrong date. Well, they have to be able to change that. Or somebody changes their password. Well, they need to be able to change that in the database too. But the last one, query, that's probably the most common and the most important of these database operations. Sometimes modifying happens more, depending on what you're doing. But in most cases, mostly what you're doing is asking the database questions and getting answers. And that's what a query is. So for example, every time you go to Facebook and Facebook wants to pull a bunch of data to put on your feed, basically they're doing a set of queries, right? They have to run some query to get the batch of who your current friends are, all the things that they've done in recent time. They run it through some optimization algorithm to show you the things they want to see. But basically, they're running a bunch of queries on the database to pull stuff that they've done. Say, so here are your friends. What interesting things have your friends done lately? Each one of those is a separate query. And queries, again, very important because typical databases tend to read much more often than they do write operations. People tend to look at what's in the database way more often than they actually make changes to it. Now, in a relational database, other systems too, but particularly relational databases are designed for this, that you can have queries going across multiple tables. You know, of course, a query can just ask for one bit of information, like say, looking in this table of users here, given the email aa1@gmail.com, what's their birthday, right? Or given their email that they enter in to log into the system, does their password match what's stored in the system? Something like that. Okay, so that's a single table query. But of course, you can also do multi-table queries. Like imagine if you have one database table full of photos and another database table of users that includes their location, then you could do some cross-link. If every photo is associated with a user who uploaded it, then you could run a query like, show me the whole batch of photos viewed yesterday by users from Chicago, right? And in that case, you have to integrate data from the two tables. Part of it from the user table, identify which users are from Chicago, and then looking at the photos, check every photo to see, oh, is this photo posted by a user who was from Chicago? And there they could integrate that and give you the results. Yeah, anytime you ask the database a question and you get an answer, that's a query in some sense, yeah. So like you go to Amazon and you type in a search, right? Say you're looking for 3D energy drinks and it brings you some results. Guess what? You just queried their database system, right? You go to Google and you type in a search for 3D energy drinks, right? What'd you just do? You gave Google a query that they executed for you, right? Yeah. Queries, they're all around. Anytime you ask a database a question and it gives you an answer, you just did a query. Okay. So next thing, structured query language. By the way, the CS people, they do send it, instead of saying query, they say query. So I don't know, I have noticed that. I say query because whatever. But don't get in somebody's face if they say query. You will hear that too. Structured query language, or SQL. This is another thing, right? SQL, some of the old guys, they'll call it SQL. People who are not old tend to call it SQL. And I'm kind of right on the edge of that. So I started off calling it SQL, and then all the young people started calling it SQL. And I was like, yeah, okay, I go along with that. But still, some of the old guys in our department call it SQL. Anyway, it's the standard language for coding relational database operations. So anytime you have this application that has to ask a database questions, SQL is the language that you do it in. Anyway, but live and let live as far as how people pronounce it. Don't hassle people. If you go to some interview and you get interviewed by an old guy and he starts asking you, what do you know about SQL? And you're like, well, for starters, I know that we call it SQL. Yeah, you're probably not going to get a follow-up call about that. Anyway, so SQL contains command groups for obviously queries, data manipulation like inserts, adds, deletions, modifications, all that, and other things like managing data structures, right? Creating or modifying entire tables or columns. And finally, data control language, like controlling who can access it. So you might have one user who only has read privileges. They can run queries on the system, but they can't update it. You might have another user who has read and write privileges. They can actually go in there and change things. All right, so that's what SQL is. It's the language of databases, and all the stuff that we talked about that you need to do for databases, there's ways to do it in SQL. Okay, next, key fields. All right, so one of the issues with a database, when you're running a query, you always want to get the right answer, right? And ideally, there's one and only one correct answer, and one way to get on the road to enforcing that is to have a key field that uniquely identifies each record. Okay, so the key field is never duplicated within a table. So if we go back to our image here, if you have a Facebook account, how are you uniquely identified? How does Facebook uniquely identify each Facebook user? And what is the username? Your email, right? So if you go into Facebook based on an email that's already in use in Facebook, they're going to politely say, sorry, you cannot create an account for this email because one already exists, right? That's because email is a key field. Facebook says for any one user, we are going to uniquely identify that person in this whole massive table of billions of users. We're going to identify them uniquely by their email. And that means there's no duplication. If you have that way to uniquely guarantee that, there's only one user associated with that email, then you don't have to worry. If you run a query on somebody and say, hey, here's the email, here's the password, see if the two match up, you don't have to worry that you're going to be giving access credentials to the wrong person, for example. Okay, so key fields are quite important. Okay, a key field also might actually be one or more fields. So quite often it's just going to be one field. But in some cases, you can actually have a key field being multiple fields in your table. And you'll see some of this in the first lab exercise next week. finally, in the default setup for a database, you're going to automatically check that a key field is unique when you create a new record. So if you create a new record, it'll have to have a key field, and if you try to duplicate one that already exists, then the database will say, nope, sorry, you can't do that. That already exists in the system. Okay, so that's what key fields are. Now, you can have records in another table referencing a key field from some other. Okay, so let me give an example. Screen. Okay. So imagine you have a table of users and a table of zip codes, right? And every user has this structure: username, email, zip code, okay? And every record over here has the structure zip code and municipality, all right? Basically what city they're in. So if you want to do a query to find which users are from, I should do city and state, right? Which users are from, which city and state combo, you need to use the foreign key zip code in that table, right? So for example, if over here you have Doug, and Doug's email is dlundq1@uic.edu, and my zip code was 60001, let's make it 60601. Okay, and then there's somewhere here in this database, the zip code is 60601, and it's associated with Chicago, Illinois, right? Zip code over here will be a key field. I'm going to star it. Dun, dun, dun. He's a key field. And over here, email is a key field. So I'm going to star that one. Okay, so what you do is your database will check, oh, I know this is not a key field, right? The zip code is not a key field in the table of users, but it is a key field in the zip codes. I know that for this value 60601, because it's a key field in this table, there's only one record in that table associated with it, and thus there's a unique, city and state combo to go along with it. Okay, so that's the importance of foreign keys, and that's essentially how you do these multi-table queries. Is you'll have a field in one table that is involved in the query, and you use that to reference the other table and find, the unique matches there. Again, I know this is probably a little abstract. The first couple lab exercises, you'll go through this, it'll make a little bit more sense. You'll be like, oh yeah, we're setting up tables, we're doing some stuff, we're running queries, kind of get it. Okay, this is enough for now. We're just introducing the structure. Okay, questions on any of this stuff? I mean, you all have been kind of a quiet bunch today. Any questions on anything? Nothing? Yeah. I mean, I don't know the inner workings of Instagram, but I do, if they're pulling up lots of photos, they're going to have that same kind of hybrid system. Some of it's going to be stored on disk, it's cheap and slow. Some of it's going to be stored on RAM, which is fast, and they're going to basically distribute that by popularity. And all the stuff about churn, that's going to happen because what's popular one month won't be popular next. I mean, the principles don't really change. The hardware changes, the system, implementations change, but the basic idea that you have two kinds of memory, one's cheap and slow, the other's, fast and expensive, that's not going away. Yeah. Yeah. A table, you set the key field with the table, right? So you don't have to involve a key field in a query. For example, right, this screen. No, actually, I don't want screen. I just want slides. Okay, so like here, right, you could say, give me a list of all the ordinary names of people in this table. you can run that query and it's totally valid. It's just some of them might be duplicate, right? You might get, you know, a couple John Smiths and a couple Jose Rodriguez's and, you know, whatever. You might have I have had semesters where I've had 2 Jose Rodriguez's in the same lecture. That's kind of crazy. Anyway, yeah, let's see. There was another semester I had a couple of Hamza Khans. So yeah, duplicates do happen. Even these, you know, classes, they're not set up with a key field. But yeah, you can always do a query. Not all queries have to involve key fields. But in the case where it's important that your records are uniquely identified, then yeah. So like you call up Facebook and say, hey, my, you know, my account has been hacked. I need to update my password, right? Obviously, in that case, you need to be able to uniquely identify your account. It is very important for that query that they find exactly your account and not just anybody's. So you don't, you know, change some other user's account who happens to have the same name as you. Even though Doug Lundquist is a weird name, there have been, last I checked, there were six of us in the United States. There's also a fairly famous Doug Lundquist in Canada who's a meteorologist, a weather guy. And a couple times I've gotten calls or emails like, hey, we'd like to interview you for, you know, your take on, you know, global warming or tornadoes or some shit. And I'd be like, you probably want the Canadian Doug Lundquist, not me. Yeah. Anyway, so yeah, no matter how unusual your name is, there's probably a few of you out there. All right. Anyway, okay, good. Next up, we just got a few more slides on this database stuff. And then, like I said, we'll take a few minutes to talk about newsfeed. So atomicity. All right, one of the basic principles of database design is you should have each database field only having one element, right? It's not mandated in the structure of a database. You can have like kind of arbitrarily large blocks of text that you have to build up some secondary application to split that text up into different components. But most of the time for running queries easily and quickly, you want to have each field be one thing, right? So for example, suppose you have a field for phone numbers and you include a whole bunch of phone numbers in there, right? You just have like 4 different numbers, one for landline, one for cell phone, one for work phone, one for emergency contact, whatever, right? Unless you have some secondary application that's gonna have some set sequence on those and be able to split them apart, you're not really going to be able to know which is which for any given purpose, right? You'll ask for somebody's phone number and it'll give you a list of, you know, 4 phone numbers. You don't know necessarily which one is appropriate for what you're doing. So it's better to make separate fields for each one, right? You would have a phone number for cell phone, a separate field for work phone, and so on. Now, relational database models do typically assume all fields are atomic, and they need that in order to work correctly, so that anything that exists in the database exists in exactly one place, which means you're always going to get the correct answer to a question, right? If you are looking for a thing, you'll know there's only one place where that thing can be, so you look for it there, you find what you're looking for. The other thing is it facilitates uniform data formats. Now, let me see for a second. We'll talk about talk about it now. That's fine. After this. So next thing, metadata. Metadata is data about the data. We've talked about that. But for databases, metadata includes things like the names of tables and columns. Strictly speaking, it doesn't matter to the database what you call a table or what you call a field, right? It's still going to hold the same data. Also things like the type of data in a column, whether it's going to be an integer or a floating point number with decimal points, things in time or date format, other unformatted text, that stuff. Yeah, so anyway, all those kind of things. Weird. Why is that point duplicated? That's strange. Oh yeah, the format, that's not duplicated. Format of column data, things like, you know, the maximum value on a field or the maximum length of a block of text, like your password can't be more than 16 characters long, things like that. Now, relational databases, what you'll see is every column in a table has, for any column, every column has a standard format that's applied to every record that uses that column. All right, so I'm going to explain why that's important. And this is background. This is not really testable stuff, but I'm going to say, I'll put it here. Thank you. All right, so this is one of those background things that hopefully makes stuff easier to understand. You set a format for a column, and that format applies to every record in the table. For example, if you have a password format that specifies, max of 10 characters, that applies to every user record. Okay, so it's going to work like that. Now, the reason why you do this is for offsets. Offsets, well, I'll talk about in a second. Offsets allow much faster lookups, multiplication, instead of checking lists. Okay, so suppose all the data for a record combines to be 200 bytes. Okay, 200 bytes of data when you sum up all the data stored in all the fields, right? And suppose the offset for the password is, I don't know, 40 bytes. So basically 40 bytes into a given record, that's where you'll find the password. That means if I want to search, a record, I don't have to actually scan the record, right? I can just check the exact memory locations in RAM where I know the field will exist. Likewise, if I'm doing a query on a large table, right, to find, hey, which record matches, right, I don't need to check through every byte of the untold gigabytes of data. I just need to check the relevant offsets, right? And I don't need to look them up. So for example, suppose I have some offset for the username is 20 bytes and the password is 40 bytes. Suppose set for the username is 20 bytes. Okay, so I can just scan through the RAM, and I can, instead of having to look through every byte of RAM, which is going to take much longer, I can just check like the first byte at 20 and say, does this first byte match the first byte of the thing I'm looking for? If not, I jump ahead 200 bytes more to the next memory address where the record might be, and I check that. If that doesn't match, I check the next one. It's way, way faster to just do like offsets in a thing. It's like having a book where you just look at the top of the page and say, does this thing match? And if it doesn't, you keep on moving rather than having to scan through the entire page. Okay, same kind of principle. So this is a tremendous speed advantage that's provided to relational databases. When they're running queries, they can be really fast because this every column is going to have the same format within a table. Well, a column uses the same format across all records in that table. Okay, because of that, they can use offsets. They don't have to worry that, oh, maybe the password starts at byte 50 in one record and byte 30 in another and byte 120 in another. And so I don't know where it is, and I got to scan through every byte of every record to find what I'm looking for. Okay, so that's, again, that's not really something I'm going to test you on, but that's why they're set up that way. And when you do this stuff in Access, you'll see you create a field within a table, and it'll have a format, and that format will apply to every record within the table. Okay. Now, like I said, columns hold the same data type and format for every record in the table. But what happens when data sizes are wildly divergent, like images or videos, right? So images, you can have some images that are very small and low resolution, just a few kilobytes, if that. You can have other images that are very large and high resolution, be, double digits of megabytes. So there can be this huge gap. Well, remember, relational databases, they try to keep the field size the same within a table. So if you have some pictures that could be like up to 20 megabytes, every record in your table has to allow 20 megabytes for that field. But if most of the pictures aren't anything like 20 megabytes, that's going to be a huge waste of data, right? The vast majority of your database is just going to be empty, unused space. Does that make sense? And you don't want that, right? You don't want to pay all that money. I mean, storage isn't that expensive, but still, you don't want to pay that much. You know, you don't want to multiply the cost of your storage by 10 or 20 times that you don't really need. It's even worse for videos. You can have a short, simple video that's like, you know, a few megs versus a large, big video that might be, you know, a couple gigs. That's a problem too, right? Same kind of problem, except arguably, you know, even bigger in scale. Imagine every database record, you have to allow 2 gigs for the max video size. That means even on a 1 terabyte hard drive, you're only going to be able to store a few hundred records. You're going to need like a lot more hard drives. So that's not good. That's what happens when data sizes are wildly divergent. And it shows the simple basic relational database model is not good at solving that problem, right? There's not really a way around it, that if you're going to deal with these offsets being the same for every record in a table, then the cost of that for wildly divergent data sizes is a lot of empty space in your database, which is bad. Okay, other stuff, databases can have dependencies where one value inherently depends on another. For example, age is going to depend on birth date, city and state are going to depend on the zip code. If you have all of that stuff in the same record, then there can be problems where conflicts arise. So what you generally want to do is remove dependencies within a table. So like I had in this example, screen, but back to it. This, if I put zip code, city, and state all in the same record, it's possible that some data entry person might enter in the wrong zip code that didn't match the city and the state, or the wrong city or the wrong state that didn't match the other things, right? Typos happen, that's a problem. But by separating it, by just entering the zip code and having the zip code refer to the city and state, at least, you know, I know if this zip code is correct, then it's going to bring back the correct, you know, city and state. And number two, if there's a typo in there, you know, it's going to be a lot easier to figure out, right? For one, a lot of the typos are going to be not having enough digits or having too many digits or having a character that's not a digit. And that's very quickly going to be recognized. They're going to say, oh, nope, that's wrong format. Can't use that. Or if they enter in a number that actually doesn't correspond to an actual record in the zip code table, they're going to recognize that. So yeah, problems can still happen, but by breaking up that dependency across tables, then it at least solves that problem. Okay. Now, in general, for relational databases, they're a pretty good way to store data when data is stable, in particular when fields are homogeneous for individual objects, for individual records. That means every record has the same kind of data and its properties are pretty similar. So for example, passwords, sure, some people are going to have 8 characters, some are going to have 12 characters, some names are going to be like, you know, 8 characters long, others are maybe going to be 20. Sure, there's some variance there, but it's not like the variance of a 20 megabyte photo versus, you know, a 20 kilobyte photo. It's not going to be by an order of 1,000. So that's relatively stable. Second, if you're not adding new fields, every time you have a big database system, you know, one like Facebook size, there's going to be a whole lot of work involved in carefully calibrating it so it works well, right? As far as, you know, the way of storing what data is stored in what places. Remember, like with photos, one of the things we talked about is they have this system where everything is embedded in the URL where you're going to look up and find that photo. Well, if you change that all the photos are on different drives, then suddenly you have to change a whole bunch of other stuff about the web addresses where those objects are formed. Yeah, so that too is a headache. If you change the format of how permissions are kept in the database, right? If you add in like a new permission level in Facebook, that too might entail a whole lot of work to the rest of the database. And last, you know, with relational databases, like we said, data can be stored in some way to optimize query processing speed. That was pretty much saying, you know, we're going to allow finding information through offsets rather than scanning through the entire record to find if the data we're looking for is there. The cons about relational databases, number one, it's not flexible. It's hard to change the schema of the database. The schema is basically just what kind of structure the database has. So what tables are there, what fields are in each table, the formats of the fields, all that stuff is the schema of the database. It's hard to do that while still maintaining relationships between tables. Number two, you might have data that doesn't, in fact, neatly fit relational schema. An obvious one there is web pages. If you want to have a system that simply stores complete web pages don't have an inherent format, right? It's not like a web page is going to be username, password, email address. No, some web pages have a lot of text, some have images, some have videos, some have links, some don't. There's no, and they can be in any scrambled order. So you don't want to use an ordinary relational database to store web pages. It's going to be kind of a mess. Last, relational database systems, they're pretty fast as long as all the information you have to handle something can be put in RAM, right? But when the databases get big and the queries, the database operations start extending across multiple machines, then doing those kind of big queries can actually be super slow because all the interactions that are happening, instead of happening at RAM speed, and remember RAM is super fast, they're happening at network speed or disk drive speed, right? You have to pull data from storage, rearrange it on multiple machines, coordinate who's looking at what. That's going to add in all kinds of times and delays to the system. So again, if you have a query that's going to have to involve multiple pieces of hardware, yeah, it's going to run slower that way, and you might want to prevent that from happening. So alternatives, we'll talk about NoSQL systems. So here's a few different ones, and since I'm kind of in a rush, I don't want to get super deep into any of these, but just be aware, there's a bunch of NoSQL systems out there. Primarily what they do is in various ways, they cut some corners for relational databases. What they typically give up is the ability to run multi-table queries. So that's pretty much it for them. We'll have more to say before it's all over. And one example of that is Hadoop. Hadoop does a system for processing queries on very large tables. So remember when I said that for relational databases, it's difficult to process queries involving multiple machines, but Hadoop, one of the things that's for, so imagine, Google used to use it. Google used to use this MapReduce scheme. What they do is if you have a very large query, a query on a very large database table, but you can split that table into slices and run that same query separately on each slice, you can get the results faster because you can designate one machine to process each slice. So imagine if you have like, 10 gigabyte or 10, let's say a billion different web pages, and you want to check and see if a particular search term exists on any of those pages, any or all of those pages. Well, if you do that all on one machine, checking a billion web pages is going to take quite a bit of time, right? Even if it's pretty fast, it's going to take a little while. But if you can split those billion pages into batches of like 1 million each, run those in parallel on 1,000 different servers, right? And then you can say, at the end, you produce a list of, here's all the pages where this text was found, return that much smaller set of information and recombine it and deliver it to the user as a query result, right? You're going to get the results a lot faster. It's the same amount of work. You still got to look through all the pages, but because you're doing it on like 1,000 different machines in parallel, you'll get the results about 1,000 times faster. So that's it for this. And as promised, I do want to take just a minute to do a few slides in Facebook newsfeed. I won't keep you here too long. By the way, for Hadoop, for NoSQL, relational databases, we talked about them. You should know the properties of those, all this stuff that we've talked about. For NoSQL databases, coming out of this Facebook photo management lecture, basically it's enough to know that NoSQL databases aren't relational and they're designed to solve some of the problems that relational databases experience, right? But at this point, if you understand the relational database stuff well enough, then you'd just be like, well, they're not perfect. They don't work great in every situation. NoSQL databases are an alternative that can address some of those problems. Okay, so I want to take like 5 minutes to do news feed. I'm going to go through like maybe 5 slides, 10 slides, a few slides, and then we'll be done. And so please read the Facebook news feed notes prior to Thursday. So we'll talk about the Facebook feed, how it evolved, basic models, basic operating principles, stuff like that. Then we'll have more things to talk about, on Thursday. So in case you've never used Facebook, it has a feature called Newsfeed, or more commonly known as just the feed, right? So when you log into Facebook, it generates all that information and displays it to you, basically stuff your friends have been doing, plus ads, plus some news articles, Facebook notifications, things like that. Now, the key questions we're going to look at, number one, what determines the sequence, right? How does Facebook decide what goes in what order? What comes first, what comes second, and so on? What goes in the feed at all? Number two, why does Facebook do that? And number three, how does Facebook actually deal with the mechanics of managing and delivering the feed content? All right. So way back when, Facebook, like circa 2004, 2005, when it was still known as the Facebook, worked in directory mode, like my. So you didn't have a feed. It was just if you wanted to see what somebody was doing, you actually had to go to their page if you had permission to access their stuff. So users read what other people had on their profiles. There was no feed. Newsfeed launched shortly thereafter, 2006, and at that time, Facebook didn't have nearly as much traffic as it does now. So number one, there were fewer total users, right? It hadn't become nearly as big. And number two, there was less friend activity per user because, nowadays it's pretty common for people to have several hundred friends on Facebook. But early, in those days, if you didn't have that many friends who were on Facebook, most people didn't, yeah, then you weren't going to see that much stuff from them. So way back when, initially it was viable to show every user the complete list of all their recent friend activity, right? So if you logged in every day, boom, Facebook would generate this list of, all the stuff that all your friends had done in the last day, and that was manageable. But of course, Facebook gets bigger, right? People have more friends and some of those friends are more active. At some point, Facebook says, yeah, we can't really show you everything. I mean, yeah, if you click show more enough at, all the way to the end of the list, yeah, you will eventually see everything. But mostly Facebook tries to prioritize and throttle the feed. They're only going to show you the stuff that they think is going to be most interesting to you, unless you specifically keep asking to see more. Other stuff, advertisers, there's ads on Facebook. There weren't always ads on Facebook. So advertisers want to reach users. Users mostly don't really want to see ads. And so Facebook has to look at optimizing not only what ads are shown, but even the ad to post ratio. Because if you show a whole bunch of ads, that's going to drive people away. So Facebook borrowed from Google's PageRank system using a multi-factor formula. They called it EdgeRank. So Google's PageRank was a scheme for ranking search results, right? Which search results were most relevant to a particular search query. For this, Facebook, borrowed the name PageRank and they called it EdgeRank. And they used these three factors. So I'm going to briefly mention these. We'll come back to these. We'll start with this on Thursday to reiterate this stuff, and then we'll move on. So the first one, if you want to look at it, right, link there, edgerank.net. If you want to look at the first one, it's affinity. Affinity is a one-way connection strength. So how interested are you in this user, right? So, we all have on Facebook those people who like everything we post, always comment on something, always wish us a happy birthday. And sometimes we don't do the same to them, right? There are always people in life that are more interested in us than we are in them and vice versa. So this is a one-way connection strength. Basically, Facebook says, how interested are you in the content provided by this person? Other factors they look at with that are mutual friends. If you and somebody have a lot of mutual friends, Facebook knows you're kind of part of a group, maybe you're a bunch, and they look at how frequently you interact. The second one is weight. Weight is the significance, the importance, basically how much effort it takes to do a particular action and content. So for example, taking time to actually comment on a post, Facebook considers that more important than, just kind of mindlessly clicking the like button. So it's possible that even though there's a person that you don't interact with that frequently, if you always comment on their stuff and you always have, detailed, lengthy comments and back and forth with them, then Facebook is going to say, wow, yeah, you're really interested in what this person is saying. Even if, your affinity isn't that high, maybe the weight of your interactions with that person when they happen is going to be pretty high. And they'll say, yeah, you're interested in this. Also, pictures are generally considered more substantial. I shouldn't say comments, text. Sorry, I got to edit that. I don't know how that happened. Okay, more important than text, right? Because why? Damn it, wrong thing. Text. So people know that Facebook wants to, people on Facebook want to see pictures. And so all else equal, yeah, they're going to kind of prefer to show you pictures than text posts. And the last thing is time decay. Facebook doesn't want to show you old data. So it combines those three factors and says, hey, based on these, this is how we're going to rank what you see. So if a post is new and by someone that you're interested in, that you have a history of relevant interactions with, then yeah, Facebook is going to say this is important. It might go at the top of the feed. Okay, all right, good. We'll come back on Thursday and fill out this stuff. All right. I gotta upload that. Hello.
Hello. I'm not gonna be here Thursday.
Okay.
What am I gonna miss this summer?
Well, we'll do a big chunk of the newsfeed lecture, I'm sure. That's the best I can give you. That's probably what's going to happen.
Anything else?
Probably not. Talk about Pack. Yeah. Yep.
Thank you.
Sure. Hello.
Hello. So we got an exam on week 4.
What's that?
We got an exam on week 4.
Yes.
What is it gonna be about, the Facebook thing?
Yep. Facebook module. All the lectures in the Facebook module.
Like, how do we study it? Like, are the summaries enough, or do we have to know all the?
The summaries will not be enough. That's just preparation for the lecture. But I'll have more information closer to the exam. I'll put some study materials like about a week before the exam. So, yep. Sure. Hello. What's happening?
Eddie wanted me to let you know if you could stop by at the involvement for the IDS group.
Who?
Maddie Gonzalez.
Oh, yeah. Okay. I've never heard her called that. Yeah, maybe, but my Thursdays are actually really busy. Tuesdays are really busy. I know it's going today, but do you know what table she's at? I can stop by and say hi.
I'm not sure
Yeah.
what table we're at, but I know we have a schedule set for it.
Okay. If she can send me a note, I can
Yeah, she
pass by for a
forgot-
minute.
Yeah, she said she forgot to email you, but she just wanted to see if you wanted to stop by.